The broadcast is now starting. All attendees are in listen-only mode.
Hello everyone, could everyone hear me? If you could hear me, please click the raised hand button and we will begin the webinar shortly. Okay, we will begin our webinar today. Hello everyone, my name is Tyler Kang and I'm a CA consultant from MIDAS, and welcome to Insider's Perspective webinar. Today's webinar's topic is Tools for Efficient Modeling of Bridges with Unique Geometries by Zachary Taylor. To tell you a little bit about our speaker, Mr. Taylor is a bridge engineer from Michael Baker International, and he has finished his bachelor's degree in civil engineering at Utah State University in 2010, and also finished his master's in structural engineering at Utah State University in 2011. For his past significant projects, he has worked on Mexican Hat Steel Arch feasibility study, I-215 reconstruction for interchanges on Girder Highway, and Layton Crossing, which is a curved steel girder bridge. To all attendees, if you have any questions during the presentation, please feel free to write them down in the question tab, and Mr. Taylor will answer those questions at the end. And now I will pass over the webinar to Mr. Taylor. Thank you.
All right, I hope everyone can hear me okay. If not, I guess someone can let me know. Let's see. All right, well, thanks to everyone who tuned in for today's webinar. Like Tyler mentioned, I'm Zach and I'm a bridge engineer with Michael Baker International. Today I'm gonna show you one example of how the powerful tools within MIDAS Civil can be used to model bridges with unconventional geometries. When modeling structures with unusual geometry, finite element software like MIDAS becomes a very important, if not necessary, tool. MIDAS has developed several wizards to streamline the modeling process for a wide variety of complex structures, but occasionally we come across bridges that cannot be defined fully using one wizard or one tool alone. The purpose of this webinar is to show you one example of how the tools available in MIDAS can be used to help model complex bridges more efficiently. I will be focusing mainly on the development of our modeling approach and the MIDAS tools that we use to create our model. Without some sort of approach or direction, complex models can become cumbersome and time-consuming, not just when creating the model, but also when trying to post-process results. I hope that this presentation illustrates that to model quickly and accurately, you don't always need to have that perfectly tailored template or wizard or one-size-fits-all type tool. MIDAS offers many versatile tools that can help you accomplish your project needs, whatever those may be. So that brings us to our project, the Soaring Canyon Bridge. It's a driveway to a private residence up in the mountains above Park City, because when you have a house on the ridgeline above Park City, I mean, why not, right? So here's our bridge with a beautiful sports car included. The 5-span concrete box girder was designed as an architectural feature to the residence, and the extreme geometry was needed to meet the county's requirements for the driveway grade. So what we end up with is a 5-span curved concrete box girder with a couple of 45-foot radius curves on a 10% grade with a somewhat unusual box girder cross section with large tapered overhangs. So this kind of shows the overall final geometry in a format we're a little more used to seeing as engineers. When I first looked at the concept plans from the architect, my first thought was, I'm going to need MIDAS. And my next immediate thought was, how long is this going to take? I didn't have a very good idea what direction to go to get this modeled correctly, accurately, and get the results that I was going to need. And just like any project, any modeling project without an obvious solution, I realized I was going to need to come up with a direction first, some sort of approach. And for me, this was key. It saved me a lot of time. I knew that if I hadn't spent a little bit of time up front, planning everything out, figuring out what I needed, that I was going to have a lot of headache and time spent modeling later. So I realized that this is just one example, and I don't really expect that many of you are going to use this example as a template for your next curved concrete box girder bridge. The tools you may use might be different than the ones we use for this example, but the underlying concepts presented, I think, can be applied pretty much any project. So the first step for me was to determine what were my modeling considerations. First and foremost, we needed the beam forces for design of the concrete box girder. For this project in particular, we took the beam forces from MIDAS and used those forces to design within spreadsheets. MIDAS does have design capabilities, but we will not be exploring those for this webinar. The second thing we needed the model for was for seismic response and design of earthquake resisting elements. We also had a custom design live load criteria, since many of the trucks that we designed for on highway bridges can't even make it up the driveway because of the geometry. So we came up with our own more appropriate live load criteria. The owner also had some concerns about potential maintenance of expansion joints. So it was decided the bridge would be modeled and designed as a rigid frame, and temperature effects would need to be considered. I needed to also choose a method for creating the horizontal curvature and vertical profile, since we wanted to account for the effects of the steep grade and varying column heights for the lateral and seismic analysis. For me, one of the most important things was I wanted to avoid a post-processing party. So I wanted to find an approach that would give me the results in a format that required as little manipulation as possible after the fact. Again, your project considerations may be different from this one specifically, but identifying these things up front will help you to find a direction before you start modeling. Once the modeling considerations were established, I needed to determine if there were any design requirements that would also affect the model. And the two main references that we used for this were the AASHTO LRFD design code and the NCHRP report 12-71, which provides guidance on the modeling and design of curved concrete box girder bridges. These two references provided guidance on when to use different model types for a curved concrete box girder. The methods addressed are plane frame, spine beam, and sophisticated 3D analysis methods. Plane frame basically allows the bridge to be analyzed as if it were straight. A spine beam allows for the bridge to be modeled as one beam that represents the entire cross-section at the center line of the superstructure, with corded beam elements around the curve. And then full 3D kind of can take a lot of different shapes, anywhere from a simple grillage model to an all-plate model. The central angle for this bridge ranges from 55 degrees to 68 degrees from support to support. So that puts us squarely in the category of sophisticated 3D model, which rules out our simple plane frame and spine beam options. So of the many 3D options available, it's important to choose an option that's complex enough to get you accurate results, but not so complex that it becomes overcomplicated. Oftentimes, the more complex the model becomes, the longer the modeling process and the more difficult post-processing becomes as well. The decision of what type of sophisticated 3D model to use is oftentimes going to be based on your own unique situation, engineering judgment. And for ours, we chose a grillage method using only beam elements, since these types of models produce results in terms that are more commonly used in design by engineers, and also based on guidance from the NCHRP report, which states the reliability of these types of grillage models for concrete curved box girder bridges. The figure shown is a general representation of what a grillage model looks like if you're not already familiar with it. Basically longitudinal beams connected with transverse beam elements for distribution that are weightless but have stiffness. So the next step is to kind of dig into MIDAS a little bit. Now that we have established our design approach or our modeling approach, I wanted to experiment with what tools were available in MIDAS to quickly create my grillage model with all of the crazy geometry that I needed to get into the model. And so the first thing that came to mind for me was actually to maybe I could import the geometry from CAD, which is an option available in MIDAS. If you come up to the, I'll show you how to get to that. Come up to the MIDAS menu, import AutoCAD BXF file. Here, using this, you can import nodes and elements that you've drawn up in CAD program. It's actually a pretty slick tool for complicated, especially for it's especially effective for modeling tough geometry instead of maybe in place of a wizard. I knew for me this would take quite a while due to my lack of 3D CAD skills, so I wanted to explore some other options and just see if there was anything else available. So I went back into MIDAS and started exploring the wizard options. And the first one that caught my eye, for obvious reasons, was the grillage model. I'm not going to dig into this too much, but I will show you a screenshot of what I was able to come up with using a grillage model. And it's very rough preliminary model. And this wizard may still be a good candidate for this type of structure, but for me, I found it a little more complex than what I wanted to use. There's more beam elements than I wanted to have to process, and I found it difficult to create a more simplified model that would kind of fit our needs a little bit better. And so decided against that. I started looking at the PSC bridge wizard options, which was quickly ruled out for me because of no option for creating a curve or a vertical profile. So I couldn't really, I was starting to feel like I couldn't find a wizard or another tool that was going to work very well for me, and was starting to feel like I would need to fall back on importing the geometry using CAD, which is still a good method. I just knew it was going to take me more time than it might take someone who has a little bit better 3D CAD experience. So one other thing that I knew is that I knew I needed a model with more than one girder line, and that and we felt like we could probably model this structure using 3 or 4 main longitudinal girders is all we would need. And that kind of got me thinking a little bit that maybe, well, the steel composite girder bridge wizard is one I'm familiar with, and it does that, but it creates steel girders, obviously, instead of concrete. But I thought, well, why can't we just use that wizard to create a framework and then swap our steel girders out for our concrete sections? And so, although we don't have although we're not doing steel bridge, we just need to establish a framework to build upon. And for me, the steel composite was the fastest wizard, or the fastest way for me to get to that framework. For you, it might be a completely different approach. This is the one that we went with for my purposes. So before we could use the wizard, there's still a little bit of prep work that I had to do. And the first thing I needed to do was choose how I wanted to divide up the box girder for our longitudinal girder elements. And the two main central girders, this is how we divided it up. The two main central girders use the webs of the box girder and half of the top and bottom slabs between them, and then kind of as flanges, and then the overhang divisions allowed us to capture what was happening, the longitudinal response of the overhang areas out away from the center line of the bridge. The horizontal layout is created in the steel bridge wizard using beginning and end points and intermediate PI points. So for our bridge, the first curve requires 2 PI points because of the length of the curve around. And the second curve is short enough that 1 PI was sufficient. For the vertical profile, the bridge is one constant slope between all of the supports, so the elevations were calculated at each support to be entered into the wizard later. In a grillage model, transverse dummy beam elements provide the load path for distribution between longitudinal girders. These dummy elements provide stiffness, but they're weightless. The division of these transverse dummy elements that we used follows the guidelines found in AASHTO and NCHRP report. The central angle from between the ends of any given longitudinal beam segment should not be greater than 3.5 degrees. And for our bridge, the maximum beam segment length was 26 inches. So it'll bring us back to the model. Unfortunately, I'm not going to be able to go through all of the tools in the wizard and all the tools we go through step by step, just for lack of time. But there are many tutorials available, and the MIDAS help manuals provide a lot of good detailed information about the tools we use in this webinar. So check those out if you aren't already familiar with them. I'm going to open up our wizard here that we used. And so we're using the steel composite girder bridge wizard. So we have to select a steel composite I section or a box or tub. We just went with the I section. Doesn't really matter because we're going to change it. But and span information was entered, deck width. We chose the all frame model, which is essentially just a grillage model. Main reason for that was we didn't want to deal with all the post-processing that comes with combining plates and beams in the system. Get quite cumbersome. And we also wanted to be able to just pull beam forces out for design use. We selected the multi-curve option to lay out the horizontal and vertical control line as we showed in the other slide. This is what we ended up with. So you can see our beginning point, our intermediate points using the X and Y coordinates that we calculated, and the radius. Vertical curve was defined simply using stations along the curve, the horizontal curve, and the elevations associated at each support. We also chose to model with the substructure since we knew we'd be running a seismic analysis. And as part of this, we defined a bent cap, columns with all uniform height, which we could have identified different column heights here if we wanted to in the advanced, but we just had them generated originally with the same height. And then any support conditions that we wanted. In the section tab, this is where we defined our location of our horizontal or our longitudinal girders. The girder offsets from the center line were determined based on the centroid of each of the girder sections. That's what these numbers are. Transverse deck elements are the dummy beams, and the deck thickness is the depth of the transverse dummy beams between our members. This thickness, defined by the wizard, will be modified after our framework is created to better represent the actual transverse stiffness of the box girder. The transverse deck elements also basically define our length of the longitudinal beam segments, or our mesh, essentially, if we want to call it that. The bracing section is basically there to define any diaphragm or intermediate end diaphragm conditions. Information does need to be entered here for the wizard to run. So we put in some intermediate diaphragms and our bent and abutment diaphragms as well. Under the girder information, since we're using the steel composite wizard, we needed to use a steel composite eye girder as a placeholder, and the wizard won't recognize anything, any of our custom concrete shapes, because it's a steel girder bridge wizard. So this is what we just kind of defined an arbitrary section. Doesn't really matter. We're going to end up changing it anyway, but that's what we used as a placeholder in order to generate the framework that we want. In the loads tab, I'm not going to cover a whole lot here. We just use this to generate some of our loads automatically for us, make life a little easier. You can also define traffic lanes here easily, and any vehicles that you may use for your model. Construction staging can also be defined using the wizard. In our case, we don't have construction staging, but this is a very handy tool if you're doing any kind of staging for construction. I'm going to run the wizard here, get ourselves a nice, pretty helical curved bridge. So now that we've generated the model, first thing I did, and actually I'm going to switch models here. First thing I did was define some groups. Groups are probably one of my favorite things in MIDAS. They make it so much easier to select and modify different areas of the model without having to select every element individually or accidentally selecting the wrong elements if you have that issue, or it also makes it easier to isolate different portions of the bridge when viewing results. So you can just look at the girders or the columns alone and none of the other stuff gets in the way. So I'll kind of actually cycle through some of these for you. You can see that I can select the different girders, or if I want to look at the dummy beams themselves, or if I want to isolate a girder and set it as active. All these tools are very helpful in the modeling process. So before we ran our wizard, we defined our girder shapes that we wanted to substitute in for our placeholder steel girders. These can be defined either using, let's see here, section properties, where I can either add, there's a myriad of different shapes that you can define there, but for me it was actually easier to use the general section designer to create our little custom shapes. I'll just kind of show you a couple examples of those shapes. So here's one of our interior box beams, and then this is one of our overhang beams. These are just defined. You can define the materials, the coordinates as well. It's a pretty slick little tool to make whatever shape you end up needing for any kind of girder. And then these can be imported back into MIDAS using by converting them to an SEC file, which we did for all four. So using those new girder shapes, we can substitute out our steel girders for our new concrete girders. Oh, by the way, in case anybody's curious, the tree menus, I like to have 2 tree menus open. If you're interested in how to get there, if you right click in this space up here, you can get a second tree menu. It tends to be kind of handy when you're working between the different dialog boxes. So if we want to swap out one of our girders, say the inside overhang girder, all we have to do is select it and then assign a new girder. I will just check to make sure we did this right. And looks like we got it modeled in there correctly. So now no more steel girder, new concrete girder. Same process for all 4 girders, swap them all out, and we've got ourselves concrete bridge instead of a steel bridge. The next thing that we needed to do is define our transverse dummy beams. So currently they're all represented, and actually I'll show those to you now, just as rectangular 8-inch thick beams. As you can see from the way that this looks here, there's a lot of overlap on the inside curve, and there's some gaps on the outside. We wanted to account for that and get the stiffness right, make sure that we were accounting for our transverse stiffness the right way due to the curvature of the bridge. So we tapered these sections, and so we defined new sections for each of the overhang dummy beams, as well as the central beams that connect the 2 box girder, like between the webs. And so in order to swap these out, you just follow the exact same process. Well, first off, I'll show you how you can define a tapered section here from scratch if you were to try and do this. We use a solid rectangle. So you have 2 axes of variation, and you just define them simply in these little boxes here, and you got yourself 2 tapers, and a vertical and a horizontal taper, and that's what we did for these. So let me show you that. Selected just this outside curve here. And assign the tapered sections. What I didn't show you, actually, I'm going to delete this just so you can see what happens. But if you don't have a tapered group assigned, it will just assign each of those. I'm sure you can see this, but it'll just assign each of those beams as the tapered section definition that we defined, which is not really what we want. We want them to taper as a group. So in order to do that, you select those beams, come to Properties, Tapered Groups, assign a name. I'm just going to call it Group 1, and then hit Add, and now you've got a nice tapered overhang section, and horizontally as well. So we followed the same process again for all of the tapered overhangs, and also for the central dummy beams between the box girder webs. One thing to note about that is, I'm actually going to switch over. We had to do some modifications to both the longitudinal. There we go. We had to do some modifications to the longitudinal elements to get them to behave properly for the modeling process. Also the transverse dummy beams. So this is an excerpt from the NCHRP report, and it outlines how the properties should be modified to create the proper model response. So essentially, for instance, we have 2 channel shapes, but really it's one box girder, and the torsional stiffness of a channel shape is is so much different than a closed box girder. And so we need to make some modifications to some of the properties to get it to behave more like an actual box. Since the sections are defined as a value type, we can easily modify each of the properties based on the recommendations in the NCHRP report. For transverse dummy elements between girder webs, the dummy elements were modified according to the guidelines in the report as well. These guidelines are modify the section properties to convert the two slabs, top and bottom slabs, into one equivalent beam member. In MIDAS, this was also defined as a value tab, so it's very easy to get in and just modify whatever properties that you need to tweak to get the model to behave as desired. Unfortunately, sections defined in the value tab can't be tapered, so our central box girder elements were not able to be tapered. I'm going to switch back to the model and just show you how those can be modified. For instance, just use this overhang beam. So we imported, oh, actually, let me show you how I imported those longitudinal beam members. Never did that. So if you come to the value tab, go down to general section, you can import those SEC files that we defined earlier for our beams. For instance, let's say we want to do the overhang beam, and there you go. It brings it in with all of its section properties, and now those section properties can just be modified by hand as needed to get them to behave the way you want. Same thing goes for the transverse beams, the transverse dummy beams. So I'm going to look at the ones between the webs. So kind of like I described, it's one rectangular section for basically two, well, a top and a bottom slab, but we modified the properties. We first calculated the section properties for the rectangle and then modified the appropriate properties to get it to behave more like it should. So for lack of time, I can't show you all the modifications that we made to the model after this. Those are the main, the bulk of the changes that we made to get it to where we needed it to be. But I'll kind of describe some of the other changes we made just briefly. So we had, when the wizard generated the model, we got some extra bent cap nodes that we didn't need. So these were removed, deleted. Also, our columns were extended up to frame into our diaphragms up here above the columns. They're right now connected by an elastic link, which we also removed because it wasn't applicable for our bridge. And then the columns themselves were also lengthened to their appropriate lengths, and intermediate diaphragms that were defined were removed since they were shown not to provide significant contribution to this bridge, since the top and bottom slabs provide a significant amount of stiffness between the box girder webs. I'm going to switch to our final model here. We also added some abutments as thick plate elements. And then the last thing we did was verify boundary conditions and adjust boundary conditions to what they needed to be for our specific model. For other models, maybe not this one in particular, part of that process would involve going through and checking rigid links, elastic links, wherever applicable, making sure that they're all in the right places. Since we have the rigid frame, there's very few of these types of conditions to modify. The next thing we did was to define all of our loads, external loads, including temperature, some external decorative fun stuff, centrifugal force, braking force, all of our wind loading, lateral earth pressure behind the abutments, live load surcharge behind the abutments, self-weight of the members, some barrier weights or curb and railing weights, as well as wearing surface. All of these load cases were combined into different load combinations and then enveloped as needed. We also defined our response spectrum for seismic and our seismic load cases. Defined all of our lane locations, different combinations of vehicles in our load cases as well. And as part of those, we also had to define our control data for the seismic analysis and for the moving load analysis. I'm not going to show you any of that in detail for lack of time again, but one thing to note in all of this is that as you go along, you should always perform intermediate gut checks to verify and validate your model as you move from one step to the next. You don't want to get all the way through your process and find that you need to go back and fix something that's going to take you away from, or that might take you all the way back to the wizard step per se, and you've lost all the work you've done after you've generated your model through the wizard. And let me show you some of the results that we got here. Actually, I'm gonna. So you can see how a model like this is very easy to post-process after you've done the modeling. One thing that's interesting about this is we were able to see how little the actually the overhang beams contributed to resisting the moments. There is some contribution, but the majority of it's taken up by that interior box beam. You can also look at torsional forces you'd expect to see for a curved bridge like this. Also, we can isolate the columns here and look at some of the seismic forces that were in our columns. So overall, pulling forces out of a model like this is quite a lot easier than trying to figure out how to reconcile forces in a combined plate beam model and some of that other, although it's not necessarily a bad method for modeling, it just involves a lot more post-processing. So that's basically the bulk of what I wanted to show you. We've been able to successfully use similar process to this for multiple different complex bridge structures. And using these combinations of tools like this, we're able to expedite the modeling process quite a bit and make it a lot easier on our budgets and schedules as well. So with that, if anybody has any questions, I'll be happy to answer those.
Okay, so now I will be showing the questions to you. Give me 1 second.
Okay.
So here are the questions, and yeah, so please proceed.
Okay, so the first question is, you said you used your own loading. How did you come up with that loading, and is it more conservative than AASHTO requirements? I would say, well, so first off, we used a lot of AASHTO. We used the MBE actually for a lot of our loading. We selected vehicles from the load rating side of things that tended to fit with more with what could actually go up the driveway. So we chose vehicles that would actually fit and then ran those as the live load. We also modified the factors. It was, in a lot of cases, it was a lot less conservative than AASHTO, just because with that AASHTO you're dealing with, you know, large trucks on a freeway constantly hitting bridges hard, and this is an isolated location that hardly sees any heavy traffic. It's mostly just you know, SUVs or whatever. So, but we did want to make sure that it could accommodate, you know, moving trucks and that type of thing, construction equipment. So hopefully that answers that question. The next one is, how is the braking load and centrifugal load from traffic considered in the model? We hand calculated the centrifugal and the braking load and applied it in a way that would kind of produce worst case results. So for braking load, for instance, you notice on the shape of the bridge, there was kind of a straight section. We applied, in our load combinations, we applied the braking load all in the same direction, assuming that the entire bridge would kind of contribute in resisting the braking load. And centrifugal load, we applied individually to each column to find the worst case scenario. So there was a little bit of post-processing there and some back and forth that we had to do to figure out what was the worst case. That was just applied as a point load at the top of the column, and also a corresponding moment at the top of the column for the eccentricity required for centrifugal. Next question says, can MIDAS also import Bentley's microstation designs and models? Yes, the answer is yes. I have several colleagues who have showed us how to do this. I personally haven't used it, but it looks like a very, very slick tool for importing geometry, and I'm hoping that at some point I'll get the opportunity to get a little better at that. I'd like to see how that can work in an actual project. But yes, you can do that. It must be in a DXF format though, I believe. Let's see. Next question is, how come you didn't create one line and apply cross section? Sorry, I'm not understanding it. How come you didn't create one line and apply cross section to the whole? Oh, okay. So I kind of explained this a little bit earlier. So the NCHRP report allows you to do this for curves that have a small enough central angle. But if the central angle gets too big, it's not adequate to just run it as one line. There needs to be multiple beams applied. So one thing that might be interesting for some of you, we did look at, we compared the results that we got from our 4-beam analysis to a 3-beam analysis, where we did the box itself as one beam and then the overhangs kind of as separate beams. And we did come up with pretty similar results. It was, you know, either one probably would have been fine for our purposes. And then the last question here says, start to finish, how long, hours, days did it take you to develop your model, process, and post-process it? Well, that's a loaded question for sure. I would say that for modeling and coming up with a model and a process, it was kind of a little bit back and forth trying to figure things out, but overall modeling time, I would say 2 or 3 days tops. And then develop, I'd probably say a week of total time if you all added it up back to back. So it wasn't too bad. Probably saved a lot of time in sitting there trying to move, you know, nodes and things vertically to get my elevations right in 3D, and I'm not super skilled with that. So anyway, I think it saved me some time for sure. Post-processing, that became, I mean, that in and of itself, probably the week's worth of work trying to compile all the forces into what they needed to be, combine them as needed to put them into my actual design through the spreadsheets. Any other questions?
Okay, actually, Mr. Taylor, we're answering those questions. We actually got more questions.
More questions? Okay.
I'll just read them out to you hopefully. Since we have 15 more minutes, maybe there's a few more questions for us.
All right.
Okay, so the next question is, how did you control or enter the transverse stiffness between the box girder pieces?
Oh, okay. So I wish I could show you, but in the MIDAS model, there are, well, so for your sections, you have, if you define your dummy beam per se, that between the girders, if you define that as a value type, then you can manipulate any of the properties that you want, really. And that's basically what we did is, gave ourselves the option to change the properties as needed. I hope I'm answering that question right. But that's essentially how we handled that, and those were based off of the NCHRP report.
Okay, the next question is, can you please explain how you model the torsional box stiffness?
Oh, sure. So for the longitudinal beams, the NCHRP report covers this as well, but essentially what we did is take the entire box section torsional stiffness and divide it by the number of webs in the box. So you're getting essentially what you would get. It's just half and half for the longitudinal girders. And we verified that with a single box girder element just to see how they compared, and it was quite similar. Transverse, there were some other equations involved. You'd have to probably get into the report a little bit to fully see, or for me to, it would be tough for me to explain without getting into the report, but if you were interested to know, you could get into that report and see how the top and bottom slabs were accounted for and how their moments of inertia were modified, and kind of come up with that.
Okay, we actually have a bunch more questions, but I'll just select 2 more and then we will end the session for today.
Okay.
Okay. If all plate model were used, how do you use MIDAS to design the box girder meshed by the plate element?
That is a good question. That's one that we thought a lot about. We thought about actually doing an all plate model, but we also struggled with trying to figure out how we would design using that. I'm sure there's a way we could have done it. We just realized that it was going to take us longer than we wanted to, and we were able to get pretty good results out of what we did model, and so we didn't go that route. But I would also be interested to know how that would go. I think that would take quite a while.
Okay. The next one is, you mentioned that you computed the elevations at each support outside of MIDAS. How did you import those elevations into the model?
Okay, so we calculated those, and then in the what's the name of it? Forget the name. It's the advanced button for the multi-curve. That's what it is. Inside the wizard, there's a little section at the bottom. It's just a hand input. So we had to calculate how far along the center line the support was for a station input, and then we just had to enter in the elevation just by hand in the box in the wizard. Okay,
actually, there's one more question. There's 2 questions that's similar, so I would like to go over. Okay, so the last question is, what type of foundations did this bridge have, and what about the soil interaction and the foundation? There's 2 different questions, but yeah, similar questions.
Sure. Good question. They were spread footings for the location. Actually, it was pretty good soil up on the mountain. There's a lot of bedrock up there. So everything was on soil foundations, or spread footing foundations. And the soil interaction, we used the forces that were developed. We assumed a fixed condition, and then we considered, the effects of overturning and those types of things based on the forces we pulled out of the model. So we didn't do the actual soil interaction inside MIDAS, but we did it like you would do, for a typical spread footing outside of MIDAS.
Okay, so yeah, thank you for answering all these questions. I know there are more questions in the question box, but please, if you're still curious and would like to get the answer for it, please reach back out to us and we will give you the answer. And Mr. Taylor, thank you very much for your presentation. It was wonderful.
Yeah, you bet.
All right, thank you everyone for attending the webinar, and this will be the end of it. Thank you.